Okay, welcome to class. This is variational multiple view reconstruction. This is the chapter where we left off last time. Today we'll look into how to use variational methods for 3D reconstruction. And 3D reconstruction is, if you consider it as a dense optimization problem, a problem of shape optimization. And so the challenge is to optimize the geometry of the object in front of the camera so as to give a reconstruction of the world that is most consistent with the images. And as I said, we'll actually for now focus on the setting where the camera parameters are known, where you don't have to estimate the camera parameters, so you have a set of cameras which you pre-calibrated. And then you acquired images, and so all we are focusing on from the structure and motion problem is the structure part, but to reconstruct geometry densely. And as I mentioned last time, there are explicit and implicit representations of geometry. And so examples of explicit representations, one of the most popular examples, and a fairly old one, is that of splines that were developed in, I believe, the 50s or 60s to model surfaces of cars. In the French car companies, there were several independent developments of these spline surfaces. How are they defined? Well, these are parametric models of shapes. This is for curves. For example, you have a set of basis functions, bi, and then it's just a linear combination of these basis functions that defines the shape. And these coefficients that define the linear combination, ci, they are so-called control points. In RD, if your curve lives in the d-dimensional space, here you see an example in R2. These black dots are the control points, and the curve that is spanned by these control points, C of S, is this curve in between. There are different kinds of splines I mentioned. This is called a B-spline. It's an approximating spline, not an interpolating spline, meaning that the control points are not necessarily actually attained by the curve, but it basically goes in between these control points. And the way you can see it, I mentioned it last time, is if you wiggle a little bit on this control point, it perturbs the curve in that area. In a certain area, that is, and the area where the control point affects the curve is actually defined by this corresponding basis function. And so these basis functions define the area of influence for each control point. And you can see the control point 2, for example, if you look at B2, has most influence in that parameter domain, and its influence decreases the further away you go. And so this control point is likely to have its major impact here, and further away it has less impact. And if you use these kinds of quadratic B-spline functions, so these are piecewise parabolas, then you get a smooth curve that's differentiable. If you use just polygons, so just straight lines, piecewise linear, then what you end up with is a polygon. You can then generalize them to surfaces. This is an example of a spline surface. And if you do that, then actually you have to distinguish between open surfaces that have a boundary and closed surfaces like a sphere that have no boundary. And you can define open or closed depending on how you select these basis functions. For example, if you want something that is closed, then you have basis functions as shown here, also in the previous slide. You see they are cyclic in nature. So once you reach the end of your parameter interval, say 0 to 1, then the basis function Bn starts here and it comes back down there. Right, and so you see that these basis functions it's much like defining them on a circle actually. And so you can talk about these basis functions as mappings that basically map the circle into R, and that way you have your parameter interval is closed. Whereas if you take an open interval 0, 1, and let's say you do not loop them around, then you get open surfaces, open curves. You get the surface basically by taking a product of these curves. So you have a grid of control points Cij, and then basis functions Bi, Bj. And you have two parameters, S and T. And so if you move around in your parameter interval with S and T, basically you get to different points of this surface. So you can think of S being that dimension and T spanning this dimension of the surface. And similarly, you can define higher order splines as you like. And so what you see in particular is once you fix one parameter, let's say you fix S, for fixed S, the remainder is actually a spline curve in T, where these are the basis functions and then times Bj of T. So if I fix S, let's say this is S, then if I move in T, I get the spline curve in that space. So this is spline surfaces, spline curves. These can be used to define shape explicitly. As I mentioned, in optimization, people have moved for various reasons towards implicit representations. Actually, both representations are used today. Here is an example of an implicit one. This is a simple indicator function, which basically is 1 if you're inside your geometry, your surface S, and 0 outside. So this is an extremely simple representation, simple yet very powerful, where you can represent the shape, a closed surface S, by saying U is 1 inside and U equals 0 outside. And so that way you can separate an interior and an exterior by this indicator function on the set. One of the advantages of such implicit representations is that you can define objects with different topology. So if you have an object that contains multiple components, maybe this one and that one, you can still represent it with the same representation. It doesn't really care what the topology is. You just label inside and outside, and you can then represent objects with multiple components or objects like a ring, for example, that are multiply connected. And this is very nice. So if you, for example, do reconstruction or segmentation and you don't know what the topology is of the object in front of the camera, you can start with an arbitrary topology, and if you evolve this indicator function, the topology can change. So it can create splits and merges. You don't have to actually deal with that, whereas in an explicit representation, this is tedious. Another implicit representation that is quite popular is the so-called sign distance function, where you exploit the fact that rather than assigning just 1 or 0 inside and outside, you can assign positive and negative values that will tell you how far you are from the curve or from the surface. Meaning, for a point X here, I will compute the distance to the closest point on the shape, D, and then I will assign to this point, phi of X, I will assign the value D of xs, this distance d, if this is s, d of x and s. Right, and I will assign, let's say, minus d of x and s if I'm outside, and plus the distance if I'm inside, so I can distinguish not just inside and outside, but I can even tell for any given point, by looking at this representation, I can say how far is it from the boundary. This may be useful in some cases. And what's also useful is you can actually compute such distance functions quite efficiently. There's a variety of algorithms that can be used. And there's, for example, in MATLAB, there's the command bwdist that computes the distance function. If you want the sign distance function, you still have to distinguish inside and outside, but that's easy to do. So that way you can encode shapes implicitly. Here are some advantages and drawbacks. The implicit representations typically require more memory, and typically the evolution of implicitly represented shapes is more numerically tedious, because you have to update this indicator function for all voxels, so you have an additional dimension, right? So rather than representing a surface in R3 as a 2D object, you represent the 3D volume, so you have a three-dimensional space to store in memory and to update over time. And so, of course, there are efficient techniques like octrees, etc., to do so, but nevertheless, it's a little bit of a drawback. The advantages, on the other hand, of implicit representations are quite prominent, in particular when it comes to optimizing geometry. First of all, I mentioned you can represent objects of different topology. You do not depend on a choice of parameterization. I mentioned that last time. If you have a polygon, for example, then you can renumber the points of the polygon and you get the same shape but with a different representation. And in fact, you could even add points here, and that would not change the shape, but the representation would be different. And so this is called a reparameterization, and this is to actually remove this degree of freedom in the optimization is difficult. Meaning, when you optimize for shape, you want to make sure that you can identify if two different representations are actually representing the same object. And so in representation and optimization, ideally, you want to get rid of these degrees of freedom. You want to have a unique representation. The same object should be represented with the same mathematical representation. The topology can change. I can have any number of holes, any number of components, it doesn't matter. With an explicit representation, you have a parameter interval, say the circle for a curve, for example, and then if you want to split it, then you have to change the parameter interval. This is also tedious. Another thing is, in practice, we'll see an example today. Many shape optimization problems, once you represent them with an implicit representation, they turn out to be convex, which means, as you may remember, that we can actually compute provably optimal solutions. And here I'll show you how that works in practice. Here is an example of multiple view reconstruction. So we want to recover the geometry from multiple images. And as I said, we want to do it densely, so we have two or more images. We observe points in these images. We observe their color in the different frames. And now we can assign to each point in that volume here, where we want to do the reconstruction, we can assign to each point what's called a photoconsistency. And that's a function rho, which takes values in some predefined interval, say 0, 1. And the idea is we want to distinguish points like this red one that are on the surface, and so we can expect that the color we see when projecting the point is actually should be the same ideally. And we can distinguish these points, say from the green point that is not on the surface but say inside the object. Once I project this into the pairs of images, then I see colors, namely these two colors here, that will generally not be the same. Of course, there are some assumptions that go into this approach for 3D reconstruction, distinguishing points on the surface from points not on the surface. The first assumption is that the points are actually visible from the two cameras. Let's say I have an object like this one, it's closed here. A point on the back of this object, once I project it into the two images, I will typically not see the same colors, although the point is on the surface. And that is, of course, because I don't actually see that point from the cameras. So I'm assuming here that the point that I consider is actually visible from the two cameras, and I am assuming that the object is Lambertian. That's the second assumption, meaning the color doesn't depend on viewpoint, so the color of this point, independent of how I look at it, should be the same. And the third assumption, so there's three assumptions. The first I said is visibility. The second assumption is that Lambertian, that the object should be Lambertian. And the third assumption is that I say the object should be textured. Because assume the object has only one color, it's completely constant color. Then these 2 points would be the same color, right? And so that means I can no longer distinguish if a point is on the surface or not by comparing colors. This is the classical problem in 3D reconstruction from images. If you have a completely white world, you cannot recover geometry. And so this is of course required. We have to have some coloring on the world. Of course, these assumptions don't have to be exactly fulfilled. The idea you'll see in a second is to set up a cost function, and then if they are more or less fulfilled, the approach is likely to work. Meaning if there are some shiny aspects that are not perfectly Lambertian, ideally it's not too bad. And if some cameras do not see a certain point, then I can also, cope with that. Here is how I formulate, or how this can be formulated, and this has been done by a number of researchers. In particular, one of the pioneering works here in the continuous setting is that of Faugeras and Kiriven in the late 90s. The idea is that you set up a cost function where you integrate, for any surface S, you integrate that photo consistency along all points of the surface. So you have to think, we first compute for each voxel in our space, for each volume element, we compute that photo consistency, we project the voxel into pairs of cameras, compute color consistency, and assign some value rho to that voxel. And once we have computed that function rho for any surface S, we can measure what is its overall summed photo consistency. If I sum the photo consistency for a given surface, then for that surface I can say how photo consistent is that surface. In the sense that for a surface that is very photo consistent, a good reconstruction, I should have small values of rho. So here for the green point, rho is large, is around 1. And for the red point, rho ideally is around 0. And if that holds for all points on the surface, then the surface integral for a good surface should be small. Maybe one point to note here is, assume we have a purely white world. Assume we have areas of the shape where there is no texture. That can happen. What is this approach going to do? If there is no texture, then rho will be constant. All colors will be the same. If you do color comparisons, you will always get the same value of rho. So for constant areas, for constant color areas, you expect rho will be constant. And then what happens is this boils down to a Euclidean surface area. Meaning this approach, in the absence of texture, will compute minimal surfaces. Very much like a soap film. I mentioned that earlier in class. Soap films are surfaces that minimize the surface area. And so this is a minimal surface approach. In fact, you could call that a weighted minimal surface, where locally each surface element is integrated, but it's weighted by that photo consistency function. And so it's a weighted minimal surface approach. And these are quite popular in shape optimization. The key problem with this approach in our setting is that the global minimizer of this problem is the empty set. And that is simply because if I take no surface at all, say the empty set, then the integration domain is the empty set, and then I get 0 energy, right? The cost of the empty set is 0. I mentioned rho is always non-negative, so no matter what surface you take, you will never get below 0 with the energy. So all energies are typically larger or equal to 0. If the empty set has 0 cost, it means it's the best you can do. And this is quite known. It's a key drawback of these minimal surface approaches. And sometimes it's referred to as the shrinking bias, in the sense that a smaller surface is always preferred to a larger one. How can we cope with that? There's actually many techniques that people propose. For example, the Fourgeras-Kiriven work, they initialize the surface and then only locally minimize it and compute a local optimum. If they were computing the global optimum, it would be the empty set. Which means their solution, but nevertheless one could argue this has a drawback in the sense that of course once you define a cost function, the idea is that lower cost means better solutions. And it basically shows you that something is fishy with this optimization problem. And so we came up with the solution that I wanted to present. It's a solution that we came up with around 2008. The idea was we looked at this optimization problem. Here it is a little bit more compactly, this minimal weighted surface. And we said, why is the empty set not a good solution? Let's say we take images of some object. We put an object on the table, we move around, we take pictures of that object. We see an object in every image. And then the computer tells us there is no object. That clearly is fishy. So the question is, how can we impose the knowledge that we see an object there? And so what we assume here is that in addition to the images, someone also gives us the silhouette of the object. That is, in each image we outline the boundary of the object. And we know in this area of the image there is object, and outside there is no object. And now we impose that constraint in the optimization. And this is what you see here. As a constraint, we say for all images, let's say we have little n images from 1 through n, I equals 1 through n, the projection of the surface S should match the silhouette. That is to say, if I take this object and if I project it into the image, then the projection of the surface should match the silhouette in the image here. If this is the input image, I have the silhouette area, and I know once I project this surface S onto the image, it should be consistent with the silhouette I observe. This is a somewhat abstract formulation. The question here is then, of course, once I've formulated this, is now a constrained optimization problem, and as you see, it combines this aspect of photo consistency with the aspect of silhouette consistency. And so it's ideally what we compute is a photo consistent surface that is also silhouette consistent. And of course that will remove the empty set as a solution, because the empty set is not silhouette consistent. Now that we've phrased the optimization problem, the question is, how do we represent the entities? And as I mentioned earlier, an implicit representation has advantages because problems often become convex. And so this is what we show here. If you use an indicator function u that labels the world as 0, 1, basically 1 inside, 0 outside, then if you rewrite this optimization problem with this indicator function, this is what it looks like. It's a little complicated maybe at first glance, in particular if you're not so familiar with this domain of optimization. What you have, but let's look at each term individually. What you have here is called, as a function of u, is called the weighted total variation. The integral of the gradient is called the total variation of u. And once I introduce a weighting rho, then it's called a weighted total variation. Why is the weighted total variation the same as this cost function? Well, let's look at it. I said u was 1 inside the object and 0 outside the object. Then the gradient, the derivative in space, is actually 0 most places. If for any point here, for example, u is constant 0, so the gradient is 0. In here, the gradient is 0. The gradient is non-zero only on the boundary. At points of the boundary where u changes from 0 to 1, the gradient becomes non-zero. In fact, strictly speaking, it becomes infinite. But in a way that if I integrate the gradient of u over space, then I get the surface area. So if this is a curve, let's call it C, curve C, then the integral, and u is 1 inside the curve, 0 outside, then the integral of u dx is the same as the boundary lengths of the curve C. This is a well-known fact from optimization, that this indicator function, the total variation of the indicator function of a set, gives me the boundary area of the set, the length of the curve, or the area of the surface here. And not surprisingly, if I introduce the weighting here, so each gradient at location x is weighted by rho, then this will give me exactly the weighted surface area. Now let's look at these constraints. I said the projection of the surface should match the silhouette. What does that mean? If I boil it down to individual rays, here is an image. This is the surface, this is the projection into the image. Here's my camera, this is the image plane. Then let's look at this single ray. So Rij is now a ray through pixel j of image I. So each image I has a set of pixels j, and this is the ray Rij. And now for that pixel j, here it is, I can check, is that part of the silhouette area, of the object area, or is it part of the background? And there are actually two cases. If it is part of the object area, then the ray intersecting this point from the camera center should intersect the object somewhere. I don't know where, but if I see object in a pixel, then I know if I move along this ray down out into space, then I should hit the object at some point. Right? Alternatively, if that pixel is not part of the silhouette area, if I see background color, then I know if I move along this ray, all voxels along the ray must be background. Otherwise, I would not see the background color. And so I can say all these voxels should be background. How can I phrase that as an optimization problem? I just said it. If you take a ray where the pixel is in the silhouette area, j is in the area of the silhouette part of the object, then there must be at least one voxel that is on, meaning if I sum all the values of u along this ray, then the sum must be larger or equal to 1. Could be one voxel on, could be more, but at least one must be on. Whereas if the pixel is not in the silhouette area, then I know all voxels must be 0, meaning the sum of these voxels must also be 0. This is in fact equivalent if the sum of these u values are only 0, 1 valued, right? So if the sum of them is 0, means every individual one is 0. This is equivalent actually. And so these are the two constraints, and in the optimization I can even use that fact and simply set all these voxels to 0. And then the only constraint that I really have to treat and deal with is this constraint, which says for any ray that goes through an object pixel, the sum of values along that ray must be 1. What's interesting is this is, as a cost function, convex in U. Why? Because the gradient is a linear operator, and the norm, you know what the norm looks like. The norm simply looks like that, right? So if I have, say, S here, then norm S is clearly a convex cost function. It's not differentiable, but it's convex. And these are also convex constraints, right? These are actually, if you look at them as a function of u, this is a linear constraint. It's just a sum of u values larger or equal to 1. So this is a very simple linear constraint. Similarly here, a sum of u values equals 0. These are linear constraints, which means we have a convex problem. At least the function is convex. These constraints are convex. The only thing that is not convex here is these indicator functions. Indicator functions are not a convex set, meaning if you take two indicator functions, functions that take values 0 or 1, u1 takes values, so for all x takes values 0 or 1, and u2, let's say of x, takes also values 0 or 1 for all x. Then if you take the sum of the two, for example, or the weighted average, this will typically not, it will typically have values 0, 1, and 1/2, right? Because if one of them is 0, the other one is 1, then you get a 1/2, meaning the convex combinations of indicator functions will not be indicator functions in general. And that means the set of indicator functions, the set of all functions that are 0, 1 valued, is not a convex set. That is bad for optimization because it means the overall problem we are solving here is not convex anymore, because convex problems must have not just a convex cost function, but the domain of optimization must also be a convex set. Here, this is not the case. What can we do? Well, we can just say we'll ignore that aspect of non-convexity, and we will allow real values between 0 and 1. And so the domain of optimization, if I write it down as a D, this kind of relaxed domain now is functions u that take values not only 0 and 1, but in the interval of 0 to 1. I just enlarged the space of feasible solutions by taking this, what's called the convex envelope, the convex hull, sorry. And then you have these linear constraints. These are convex in particular. And so what you have is now a convex domain. And this is what I call the silhouette consistent configurations, real valued labelings that fulfill these sets of constraints. And these form a convex set. Almost by construction. These constraints are convex, as I mentioned. And this constraint, we just made it convex by allowing real values. What does that mean for the shape optimization problem? It basically means rather than partitioning the world into a hard decision of object and background, we allow some kind of soft decision where each voxel is labeled with some real value, where 1 means object, 0 means background, and if the value is in between 1 and 0, it means the algorithm, loosely speaking, is not exactly certain. So maybe it's almost like a probability, you could say, that a voxel is object or background. And so this is in some sense a relaxed problem. This is called relaxation if you drop a constraint. The constraint, namely, that you should have binary values. This is in optimization generally a hard constraint for many problems. It makes it a difficult combinatorial problem. And here it's relaxed, meaning we drop that hard constraint. Combinatorial, why combinatorial? Well, obviously, I discretize my world into lots of voxels, and each voxel could be object or background. And so the space of all possible shapes, if I have n voxels, large n voxels, each voxel could be object or background, so I have 2 to the power of n configurations, or shapes in that discretization. So in this discrete setting, once I have discretized my volume, then the labeling is in some sense a combinatorial problem, and what we do here is we relax that to a convex optimization problem. With the drawback that what we're computing is not a hard decision any longer, but a soft decision. And so what we do in practice to solve it is we solve this convex problem, meaning we minimize this weighted minimal surface over that convex domain. So a convex cost function minimized over a convex domain, that can be done very efficiently today. There are fast algorithms that can be used. I will actually not discuss algorithms in this class. If you're interested in these applications in this domain of research, I'm teaching a class on variational methods, and there we will actually look a little more into algorithms as well. Here I will simply say one can minimize such algorithms quite efficiently and then compute solutions that are real valued. So each voxel has some real value between 0 and 1. And now what do we do to get a binary labeling? We just threshold, right? So let's say you have your spatial variable x here, the domain v, and then here is my function u. It's real valued in the interval 0 to 1. And what do? I threshold u to get a hard 0-1 decision. I take some threshold theta, and for all values that are below theta, I set them to 0, and for all values above, I set them to 1. And so you can imagine that if your function, the real valued function, is almost binary, then this thresholding doesn't really change the geometry too much. And so you can compute, in fact, you can compute the cost for that real valued function, and then the cost once you thresholded it, and compute the difference, and that gives you what's called an energy gap. In the sense that if I have, say, my energy scale here, E, then the relaxed solution has the energy E relaxed. The thresholded solution, E thresholded, has this one. And now the optimal binary solution has a cost that is the lowest possible cost among all binary functions. And so it's invariably here. Optimal binary is here in between these two. Why? Because the thresholded solution is a binary function, and so it will have an energy that is at least as large as the optimal binary one. At the same time, the relaxed solution is the lowest possible energy, not only over the binaries, but over a much larger space of real valued functions. And so this is strictly, definitely below the binary one. And so the optimal binary one must lie in between. And this is a gap, delta, that we can compute. And so it will give us, in some sense, a confidence about how good is our solution. How accurate. And in contrast to local optimization methods, this is what was done before in the continuous setting. The advantage of this convex formulation are twofold. First of all, we don't need an initialization because we have a convex problem, and so no matter how we initialize, we get solutions that are independent of initialization. And secondly, another advantage is that once we have a solution, we can compute an optimality bound. We can compute how far at most are we. So this is the distance from the optimal solution, right? And we know this is less than the distance between the relaxed solution and the thresholded. So we don't know where that energy is, but we have these two energies, and we know the optimum is in between. Here are some examples. This is 3 out of 33 photographs that you can actually download from the internet that Yasu Furukawa provided. and it actually includes the calibration as well. So this is perfectly suited to do multi-view reconstruction, and it's one very nice example, what I mentioned a number of times already. Nowadays you can do computer vision and you don't need a camera. Everything you need is on the internet. You know, you don't even need to have calibration algorithms. People have already calibrated sets of data, and there are even calibration algorithms that you can download, like the bundler software, for example. So even if you have images from the internet, there is software to do the calibration. And then you can focus on the problem that you want to solve, namely dense reconstruction. And so this is what we do here. We started with that data set, and these are the reconstructions, some views of this reconstruction that we computed. And so what you see here is we get fairly good geometric detail. The hammer is there, the sword is there, lots of fine scale structures are preserved. And in fact, these are preserved due to the silhouette consistency. Because minimal surface approaches, what they tend to do is they will typically shrink and remove fine scale structures, because that saves on surface area. And so the fact that this hammer is actually connected here is actually due to the silhouette consistency. And moreover, what we get in this optimization are reconstructions that are provably silhouette consistent. Because once we threshold these solutions, we can choose a threshold, this is detailed in the paper, we can choose a threshold which is such that the silhouette consistency is still preserved after thresholding. Meaning these constraints are still valid even after thresholding. And so we get something that is perfectly silhouette consistent, meaning if you project these into an image, you get the exact silhouette out. Here is more examples. This is images from a statue. This is actually pictures that we took ourselves with the standard digital camera. We moved around the object, we took pictures. You see we put a white background here. Why? Because the algorithm needs silhouettes. And estimating silhouettes in a nasty real-world setting is very difficult. And to make our life easier, we put a white background. That way we can automatically extract the silhouettes afterwards. I'll show you some videos. So here's one example. This is a statue that we reconstructed from this set of images, typically around 25 to 30 images. And what you see here is you have quite a good level of detail, lots of the geometric details, the folds are there. Here's another example of a statue we reconstructed. And again, maybe to point out some aspects, what you see here is the topology, as I said, is not fixed. So this object, for example, has a topology of a torus. It has a hole, but the algorithm doesn't actually care in some sense. It minimizes this weighted surface area with a silhouette consistency constraint, and it doesn't actually care what the topology is. Here you have an object that has two holes, for example, and this is nice that you don't have to deal with aspects like topology. Maybe one comment about this project. This was a project in collaboration with a museum at the University of Bonn. The question that art historians here are interested in is, this is a set of statues, about I think 18 statues. They're more than human high, and they are distributed all around the world. So there are some in Rome, there are some in Bonn, there's some in Paris. They're kind of distributed all over the world. What is known today is that they formed an ensemble. What is not known is how they were related to each other in this ensemble, how they were placed. They have some allegorical meanings. Some of it is known, a lot of it is lost. And one of the challenges that art historians are trying to resolve, a bit of a riddle, is to figure out how were these statues, what did the ensemble look like? Which statues were together, which ones were looking at each other, etc. And there are many there's a lot of information that you can use about the allegorical meanings of these statues, but also about the statues themselves. For example, one thing that you see in these statues is that they have a different level of textural detail in the front and the back. Here there's almost no text detail. Here there's a lot of detail, the face, the folds in the back. It seems like they didn't want to waste time on the back, which indicates that this ensemble was to be viewed from one vantage point. And so it gives you information where the viewer should be standing. For example, here the viewer should be looking from this vantage point. And now what you want to do is you want to try out different configurations as an art historian, but if these statues are spread over the world, you can't just get them in one location, and they're super heavy and huge, so you can't just move them around. You know, moving 17 statues around all day, you'd go crazy, right? And so they said, can you not virtualize these statues? Can you not create computerized models? And we said, sure, we'll just take some pictures and we'll plug that into our algorithm, and what comes out is a 3D model. And then, of course, on a computer you can do that efficiently. You can click each object and then rotate it around and place it down again, etc. And so the idea of these techniques is to facilitate the life of art historians. But of course, the other thing you can do is you can then have virtual museums where people can go online and basically rotate an object on the screen. And as you know, this already exists today. And with these techniques, we can capture geometry and we can capture the color. And this is what I want to briefly mention now. How do we estimate the color on the objects? So far in this class we only talked about geometric optimization, optimization of geometry and of the camera motion. But what if you want to compute the color? Right? If I just wanted to compute the geometry, if you want really accurate geometry, take a laser scanner. At least to my knowledge, you can currently not beat the precision of a laser scanner. They are very expensive ones. If you have enough time to scan it off, then you can do it. What I'll show you now in the last two parts of this lecture is the things you can do with cameras that you cannot do with a laser scanner. The first is the laser scanner by itself doesn't give you color. It just gives you geometry. Of course, you could then add a camera and, calibrate the laser and the camera. That has been done, that works. But the advantage of a color camera is that it gives you everything. So you can estimate the geometry from images and you can estimate the color. I say everything. This is, of course, as you know, simplified. If we have an object that is not textured and only has one color, then, the images will not give us the geometry. Did you have?
Those statues were all not textured, but you made the assumption that you need.
So, yeah. They're not textured. That is partially true. First of all, a lot of these statues, if you go very close, there is some texturing. The challenge actually that you have to resolve to make these algorithms work, and this is key to practical performance, is when you define this photo consistency function, rho. I said you check the color similarity. What you do more specifically is you take a little patch around these points and you do a patch comparison. And so even if the local color is the same, but in the vicinity the colors vary, you can identify that. And you can define patch comparisons, for example, which are robust even if your object is not Lambertian. then if you have a certain patterning, this may be preserved. Even if the color from one point to the other does change a little bit, then you can define patch comparisons which are robust to certain nuisances. And here, for example, if I take a certain patch, then I will see the folding in that patch. So even if the object is uniformly colored, but there is an illumination, then you see these shading effects, right? And these appear as a texturing, sort of. If you change the illumination, yes. But if you keep the geometry fixed and the lighting fixed, then the shadows don't change. All we move is the camera, so the shadows are not moving. This is a good point. So in this setting, it is not the same whether I move the camera or move the object. I always said this is interchangeable. For geometry reasons it is, but for estimating color consistency it makes a huge difference. You don't want to move the object unless you move the lighting around with the object. People have done that. And so this means in these settings you really want to move the camera and not the object to assure that the shading is preserved from one image to the next. And that is what gives you a lot of the local texture. Yes. So even if the surface itself is uniformly colored, once you illuminate it, the shading will give you the textures that you need. So to what extent it works is a question, meaning if you have a flat surface, then there is no shading, and then so if you have a flat and uniformly colored surface and the illumination is not varying across that flat surface, then you're screwed. Yes. Then these color-based techniques will not work. That said, they will actually work to some extent. What they do is they interpolate a smooth surface, as I mentioned here. And that typically is a good guess. If you don't know anything from the colors, just fill in with the minimal surface. Is not such a bad thing to do. So now, how do we estimate the color? What I'll show today is, in this class, is an approach that we proposed in 2009 to estimate the color on the surface, and we assume for this approach that we have the geometry. So we assume we've already computed the reconstruction S, we have a surface S, we assume we have a set of color images, RGB images, II, and we assume we have the camera parameters, so we know where each camera is. All we want to know is the texture, I call it texture, or the coloring of the surface. Meaning for each point of the surface, I want to know what is the RGBD value for that point on the surface. And how can I solve that? Well, there is actually different ways to do it. There is a very simple way, and people would say, well, that should solve it. It does solve the problem. You just take the images, you know where the camera is, and so you can back project the image onto the geometry, and you're done, right? There is two problems with that. The first problem is you will not find a single image that back projects on the whole surface, right? And so you will have to use multiple images and back project the coloring from the various images. These back projections in a real world setting will not exactly coincide in the overlap areas. What do? The first thing you can do is you can do an averaging of the different back projections. So for each point on the surface, I back project from the various colors that see this point, and then I do an averaging or a weighted averaging. The weighting is done, for example, you want to favor the frontoparallel cameras. The cameras that look at that patch front facing are better than the sideways cameras. And so you can give more weight to the frontoparallel, to the cameras that look straight on. This is one approach. What happens is, since the different back projections do not coincide, the averaging creates a blurring. And so the texture that you compute in this way will be very blurred. It will not be sharp. And this is a problem. The alternative that you can do is once you back project from multiple cameras, you can do what's called stitching. Meaning, for each point on the surface, you only select exactly one camera where you choose the color value from. But then you have to figure out where do I do a transition from taking colors from this camera to taking colors from the next camera. So once you move along the surface, let's say you have the surface here, you move along the surface, at some point you have transitions where you pick new colors. And these transitions, you will see them. They will form seams. You can see once you do different back projections, since they don't coincide, once you move from one to the other, you don't do averaging, so you don't have a blurring, but then you see the seams, right? And so there are algorithms which you can then run to minimize the visibility of the seams, right? I want to do the transition from this back projection to the next one, let's say if the colors are pretty much the same. And so I stick with one color, with one image, until another image gives me a very similar color, and then I can do a transition in a way that it's not so visible. But this is a separate optimization problem. It means that on your surface, S here, you will have to define a seam line where I have a back projection from this camera and a back projection from that camera, and you have to do this. Is called stitching, is an optimization problem. There is one much simpler, in many ways simpler, but definitely more elegant solution that works substantially better. And that is a variational approach. Which has, as I mentioned, all variational approaches, has a data term and a regularizer. What does the data term do? The data term basically says, find a texture T, this is the unknown, the only unknown here, the texture, such that if I take a pixel, little x, and I back project it onto the surface, this is pi I inverse. Pi I is the projection. Pi I inverse is its inverse. The pre-image, if you want, on the surface. The point on the surface. So I go back along the projection line and compute the nearest point on the surface. The texture there, if I blur and downsample it, I want it to be consistent with the input image, II. Right, so this is the challenge, and so what I'm saying is now the color shouldn't be identical to the observed image, but I'm actually modeling the degradation process that a digital camera does, at least the dominant aspects of it. And what it does is, through a real lens, it creates a certain blurring of the texture, and then it does a downsampling into pixels. And I can model that process of blurring and downsampling and say, find a sharp texture such that once I blur and downsample it, it matches the observations in that least squares sense that we have here for all pixels in each image and for all images, right? And so I have one single cost function defined for the entire texturing of the object, such that the texturing is optimal for all these images. Yes?
What does the asterisk stand for there? Convolution?
This is a good point. It is basically more than a convolution. If you have a Gaussian, then this would be a convolution, but it's a linear operator in general. It's some linear operator that models convolution and downsampling. Downsampling is some averaging. So it's not exactly a convolution, but it's quite similar. In fact, this notation is a little bit compact, but it basically means that there is a matrix operator that does this blurring and downsampling of the high resolution texture. And then I have a regularizer that is familiar to you. It's called the total variation. We've seen it before. Here is the total variation, the gradient of T integrated. In practice, this regularizer creates a smoothing of the texture. Since we don't really want a very smooth texture, but a sharp texture, the weight lambda of this regularizer is usually very small. But we need some regularizer, otherwise this spatially continuous model is not meaningful. You know, to have solutions for this algorithm, to admit solutions, we need some, for this functional to admit solutions, we need some regularizer, even if lambda is very small. What is nice about this functional, this cost function that we have here, is it's convex. The total variation, I mentioned it, is convex, and these are linear operators, and t is in here, and so this is just a linear operator, and then this is quadratic, so this is definitely convex. And that means we can actually compute the provably optimal solution for this problem. So not only do we have a single variational approach to do the coloring, but also we can actually compute a provably optimal solution for it. By the way, one little detail, of course this is the total variation, but you see a little s here. This nabla s is defined as the gradient on the surface, meaning if I move along the surface, then I check here how does the color change, not in the ambient Euclidean space, but when moving along the surface. So there are 2 degrees of freedom along the surface, and this gradient captures the change of color in these 2 degrees of freedom. It's a convex problem, meaning we can compute provably optimal solutions, and this can be done efficiently. Again, I'll skip algorithmic aspects of how to compute it. Here you see an input image. Here you see the textured 3D model. And if I tell you now, I cannot distinguish these two, I guess you would agree with me. They look exactly the same. We compute the color, but we just mentioned it earlier. You have to be careful what is meant by color. Here, the color we compute includes the shading effects. So we cannot separate the color from the shading aspects. That's because we're not actually modeling the illumination. We don't know where the illumination comes from. So we recover the sharp texture that we see in the images, and that includes the object color and the lighting dependent shading effects, etc. I mentioned that this is called a super resolution approach. Why? Because we have this blurring and downsampling that we model here. And we use multiple images, and we can actually, I'll show you in a second, we can invert that blurring and downsampling. Here is a close-up on the input, on one of the input images, and a close-up on our reconstructed texture. And indeed, you see that here we have this pixelization of these images. Once you move in sufficiently close on the eye of the rabbit, you see it, and here's the texture that our algorithm computes. And you see it's at a much higher resolution than the input images. Why is that possible? Of course, anyone who's seen CSI Miami or things like that knows that's trivial. You know, in all of these sequels, there's always the techie, there's always a case where they say recover the license plate of the bad guy, and then the head of the police department says to the techie, can you zoom in? And the techie says, sure, and he hits a button and it zooms and zooms, and everything becomes super sharp. I'm sure you've seen that many times. I always admire them, and I wonder what algorithms they have on their computers. But as you know, this doesn't actually work. You cannot hallucinate information from nowhere. So the question would be then, why is it possible here? How can we hallucinate or generate details here that are not even visible in the input images? Well, it turns out, first of all, we know a little bit how this downsampling and degradation works. Each little pixel that you see here is more or less the average color of that patch, right? And secondly, we see these downsampled images, not one, but multiple. Meaning we see the same eye here in maybe 5 or 6 camera images. And every time, what we observe is a little different, slightly different downsampled version of the input images. And from all these downsampled versions, we can actually recover the sharp original. Because the original here. So this is the downsampling and blurring that the camera does. And if we have many such images, essentially the more images we have, the sharper we can get the texture reconstruction. Provided, of course, that this operator is modeled properly, meaning we have to know more or less how much blurring and downsampling does this camera do. Or at least we have to find an estimate. For example, what we do in these algorithms for the blurring, there is a sigma, a blurring kernel, and we just select the sigma to give the best performance. And so this is what we do here, and that way we can create very sharp textures. And as I said, I believe in principle there's almost no limit as to how sharp you can do it, provided you have enough data. The more images you have, provided that they are from independent viewpoints, if the camera calibration is accurate, if your downsampling and blurring operator is represents faithfully the camera, then you can in principle increase the resolution arbitrarily. But of course, if the camera calibration is bad, if one of the cameras is off by a pixel, that will degrade everything. I should mention, maybe for those interested, one can extend this, and this is a very recent work by Aubrey and co-workers, ICCV 2011, so 3 years ago, who proposed to do texture super resolution and also estimate in better resolution the geometry and the camera parameters. Because, as I said, once the camera parameters are inaccurate, then that degrades the precision of the super resolution. And what is shown in this paper, Aubrey and co-workers, is that if you simultaneously optimize the camera locations a little bit and the texturing so as to get a maximally consistent reconstruction, then you get even sharper images. So I mentioned laser-based techniques are often more accurate and more reliable. For example, if you have no texture, no color variation, then lasers may still work. Unless you're looking at glass, then they don't work either. For glass, there is not a whole lot that you can do today, actually. There are very few sensors that can actually capture glass, ultrasound maybe, but to recover the shape of glass from images, I have not seen an algorithm that can do it. Similar actually for mirrors, that's very difficult. Mirrors are definitely not Lambertian. Mirrors are probably the most extreme non-Lambertian example, because what you see in a mirror is not actually dependent so much on the geometry of the mirror, but it reflects the world around you, and so this becomes a very difficult problem. Nevertheless, I've seen algorithms that try to recover the geometry of mirrors as well. So lasers, by and large, provide more reliable solutions, at least in many scenarios. They, in some sense, directly measure the geometry and don't have to infer it from color consistency. But image-based reconstructions have several advantages, two of them being that you can estimate, as I showed you in the previous slides, the geometry and the color on the surface. And for modeling the world, you often not only want geometry, but you want coloring, especially for understanding the world, right? If I have a robot driving around in the world and there is a sign that says no entry, I can laser scan it as much as I want. I'm not going to understand what's on the sign. Right, so that there's, in the man-made world, a lot of information on the identity and the meaning of objects is contained not in the geometry but in the color. The other thing I can do with cameras that I cannot really do with lasers, or at least that is very difficult with lasers, is I can reconstruct actions over time. Why? Because I can film an action with multiple cameras synchronized, right? So I can place, say, 16 cameras, and recently there is a company in France 4D view solutions that was able to capture with a set of synchronized 40 synchronized cameras actions. So you have lots and lots of cameras, and it's quite a technical challenge to set up and calibrate 40 cameras and then synchronize them, but that is possible. And so you can get a lot of image data, and then these cameras can be very fast. You can have cameras up to 60 frames a second or more, and once you synchronize them, it means you can reconstruct geometric actions at a speed of 60 frames a second. You cannot do that with laser scanners. It's completely impossible. Here is an example. This is a girl that is rope jumping that was actually acquired in a setup in Grenoble, in Edmond Boyer's lab. And this data is also online, so people can download. We downloaded the data. There are 16 cameras that film actions synchronously. And here are some of the reconstructions we were able to compute with our approach. This is actually, I should say, Martin Oswald, the lead author on this project, and he was able to recover very fine scale details where you can even see the rope of this rope jumping girl in the reconstructions. I'll show you some videos here that give you a much better idea than here is the scene. Here are the 16 cameras filming this action synchronously, and here you see the reconstructed geometry. And you can even recognize what's going on. So the level of detail of these reconstructions is sufficiently good to see that there is a little boy and a little girl, and that they're doing quite athletic sports movements. I guess we could have maybe used a more professional athlete, but I think this is even more entertaining. Now that you can, as I mentioned, superimpose the texture, this is just a standard color back projection, not a super resolution approach, and so it's not terribly sharp and focused. With the super resolution approach, we would get a more sharper textures. And so it's very nice because it allows you to actually follow these actions. Here's another example. Of the rope jumping girl. And so what I was actually surprised by myself is the level of detail that we can recover this rope of the rope jumping girl. And you can imagine for certain applications this is quite crucial. Sometimes these little details contain a lot of semantic information, a lot of meaning. Imagine we had recovered the rope jumping girl without the rope, then everyone would wonder, what the hell is she doing? Right? So the rope is quite important to understand what is going on. The next thing you can do with these 3D reconstructions over time is, once you texture them, there are many applications. One is you can do video conferencing, where you can transmit a full 3D model of a speaker acquired, say, with several cameras, and you can you can recover it and transmit it even in real time. That is nowadays possible, and that gives you a much better sense of being present, a sense of what's called immersion. So if you do video conferencing with someone, you can see him from different viewpoints because you have a 3D model. So you can put on 3D glasses and then you can actually visualize the 3D model so that you get a full 3D effect. And that gives you more of a sense of actually being there as well. And so all of these technologies will be coming in the coming years. The next thing you can do with these space-time reconstructions of geometry, you can use them for sports analysis. For example, if you have professional athletes, maybe a little more professional than the little boy and the girl here in these images, you can recover the action over time, and then you can sit down at the PC and basically look at this action from different viewpoints. You can stop the action, you can freeze it, you can rewind it, you can loop around, you can freely choose your viewpoint and study each detailed motion and say, well, this foot has to be moved a little higher, or here you should pay. So you can really get into very, very fine details. And this can help to give athletes a very precise feedback about what they're doing right, what they could do better. Or for dancing, etc. There's many applications. And ultimately, one application that I think will be coming as well, sooner or later, is an application that is nowadays called free viewpoint television. That's an application where you sit at home, watch your favorite movie, maybe Sunday night, and then you can choose, while the movie is running, you can choose from which viewpoint to look at the action. Right? Imagine that would be quite incredible here. For example, what I show you here, these demos here, is another demo, another example. You can see this action, and it feels like you're almost there. And what my student Martin is doing here is, while the movie is running, he pans around the scene with the mouse in real time. And he can zoom in, he can zoom out, he can go around the action and see it from any arbitrary viewpoint. Because he has the complete 3D model, the complete colors, everything, right? And so you can, here by the way, you see the ball is very specular. And this is what happens if you have very shiny objects with reflections, etc. You see the geometry is not so good. Right? So this is an example where kind of the Lambertian assumption enters, and where in order to recover more non-Lambertian shiny objects, one would have to modify the model and tackle it with more sophisticated techniques that actually capture reflections, etc. But nevertheless, you can actually follow an action, and it's almost like you were there yourself, and you can walk around it. And so you can choose, do I want to see Julia Roberts in the face, or do I want to see whoever else in the face? You can pan around and look at things from different vantage points. Of course, that is all provided that this action was actually captured by sufficiently many cameras. But what this shows us is that we don't need infinitely many cameras. 16 cameras is sufficient to get models that I can look at from an arbitrary viewpoint. And synchronizing 16 cameras, as I said, is not so difficult. It's possible. People have synchronized more cameras. Here's another example. Here you see again aspects where the geometry is not perfect. The dog is sometimes losing its legs because they're hardly visible, because the silhouette extraction is very difficult in these shady areas. And the silhouettes are not perfect, and so wherever the silhouette is wrong, that degrades the reconstruction. Another example that I want to point out is this guy has completely black clothing, which means there is no color variation. Nevertheless, we get a fairly good model of the geometry. Why? Because we have this minimal surface approach. In the absence of the color variation, it will just fill in with the minimal surface, and as you can see, that gives a very plausible reconstruction. In fact, we actually compared in these sequences with feature-based approaches. If you try to compute feature points, say on this black person, you will not see anything. There are no features. It's just uniform black. And so classical feature-based techniques will break down here. But these minimal surfaces, these dense approaches, they can still handle objects that have no features. And again, you can pan around and you can see the action from viewpoints that you never had a camera at. So you can hallucinate what would this scene look like if I were to look at it from this viewpoint. By the way, this is actually a separate optimization problem that people have published papers on. It's called new view synthesis, meaning I take views from a scene and I want to synthesize a new view. You can tackle that with a separate optimization problem. Here, however, we just tackle it in straightforwardly. We reconstruct geometry, we reconstruct the color on the surface, and that allows us to visualize everything. In fact, we can do more. Once we have a 3D model, we can actually change the colors, right? We could put a checkerboard pattern on the dog if we wanted to. It would look a little weird, but if we want, we can do that, right? So you can actually exchange colors, you can do a lot of fancy computer graphics, all sorts of things. And why is it possible? Because we have a model of the 3D world and we have a model of the colors on the object. Okay, that's all I wanted to talk to you about today in the class on variational methods for multiple view reconstruction in this last chapter, where I showed you that we can use variational techniques to generate dense models of 3D objects seen in multiple images, and even dense models of actions filmed with synchronized cameras. And I showed you we can estimate the geometry and we can estimate the colors on the surfaces even in a temporal setting. So I think this should have convinced you that there is quite some potential in what we can do with cameras, well beyond that the possibilities, say, of laser scanners. Another aspect, by the way, there is not only these two advantages compared to laser scanners. One huge advantage of cameras is they are much cheaper than laser scanners. They're typically more lightweight, and they are pretty much omnipresent. So we all have cameras in laptops, in smartphones, everywhere, and we can do quite wonderful reconstructions even from smartphones nowadays. And so there's quite some things that are coming in the next few years that exploit all of these techniques and algorithms for recovering the world from images. Thank you.